Hello, this is Sharon Kuchler, and this is my final presentation for Intro to Materials Science on the deteriorative properties of biodegradable balloons. So what are deteriorative characteristics? They look at the chemical reactivity of materials, which influence how well the material holds up in different environments over time when exposed to things like wind, water, different chemicals, physical manipulation, etc. They heavily determine what materials we can use for different projects. So for my experiment, I decided to take both biodegradable balloons made of natural rubber latex and a more traditional balloon made of synthetic latex, and then I put them in a couple different types of environment that a balloon might land in after it's released, just to see how they are affected in terms of deterioration. The environments that I chose were saltwater, freshwater, and fertilized soil to represent farmland, since these three environments make up a good portion of the surface area that a balloon can land in after it's released. The materials I used in my experiment were 4 traditional synthetic latex balloons, 4 biodegradable natural rubber latex balloons, a small planter pot, potting soil, fertilizer, enough water to keep the potting soil damp throughout the experiment, salt water, tap water, and a tape measure. Before we get into the actual experiment, I think it's important to go over the differences between the two types of latex. So the synthetic rubber latex is usually sourced from petroleum products and can include things like nitrile rubber, styrene butadiene, whose structure can be seen in the top picture on the slide, chloroprene, and many other harmful compounds. Natural rubber, on the other hand, comes from the sap of rubber trees and is mostly made of rubber hydrocarbon, and it also includes some proteins, fats, sterols, organic acids, and salts. The most common compound in natural rubber latex is isoprene, whose structure can be seen on the bottom picture of the slide. For the control of my experiment, I took one of each type of balloon straight out of the package and inflated them to 26.5 inches, and then I left them to naturally deflate for a week. After the week was up, I measured the new diameter to see how much the balloons had deflated over that time. While the control balloons were deflating for the week, I created the simulated environments that I was going to put the other balloons in. For the fertilized soil environment, I used enough potting soil to fill the pot I had about halfway, and then mixed in 1 tablespoon of the plant food fertilizer I used, per the instructions on the bag. For the freshwater environment, I just used tap water, and then for the saltwater environment, I was actually able to get some ocean water. And here are just some pictures of the experiment in progress. For the experimental balloons, I put one of each type of balloon into each environment and left them for a week. And then after that week was up, I inflated them to the same diameter as the control balloons, which was 26.5 inches. And then I left those balloons for a week as well to naturally deflate. Here are just a couple more pictures that I took during the experiment. So the results for the control balloons were that for the traditional balloon, the final diameter is 25.5 inches, and then the biodegradable final diameter was 26.2 inches. This is actually kind of surprising because I expected the biodegradable balloon to be smaller than the traditional balloon at the end of the week. So looking at the fertilized soil balloons, the final diameter for the traditional balloon was 25.4 inches, and then for the biodegradable balloon, the final diameter was 24.9 inches. For the results for the freshwater balloons, the final diameter of the traditional balloon was 25.2 inches, and for the biodegradable balloon, it was 24.8 inches. The saltwater balloons have the largest change in the diameter for the biodegradable balloon, with a final diameter of 24.2 inches, and the traditional balloon didn't have as much of a change, but it still measured in at 25.6 inches after a week. Looking at the percent differences for the control balloons, the biodegradable balloon shrunk by 1.13% and the traditional balloon shrunk by 3.77%. The biodegradable balloon left in the fertilized soil environment shrunk by 6.04%, and the traditional balloon shrunk by 4.15%. The freshwater biodegradable balloon shrunk by 6.42%, and the traditional freshwater balloon shrunk by 4.91%. The biodegradable saltwater balloon ended up shrinking by 8.68%, and then the traditional saltwater balloon ended up shrinking by 3.4%. So what do these results tell us? Based on the results, in this case, I think it would be fair to say that there was a greater deteriorative effect on the biodegradable balloons versus the traditional balloons. Going back to the definition of deteriorative properties and how it related to the chemical reactivity of materials, the structure of the natural rubber latex and the biodegradable balloons reacted more strongly with the environments that they were in, which makes sense considering the structures of both of the main components of each of these types of latex, which were shown earlier. To finish off, if I had to do this experiment again, I would definitely make a couple changes, such as making the duration longer. A week just simply was not enough time to see the true long-term effects of these environments on the balloons, since the degradation time of biodegradable balloons can range anywhere from 3 or 4 months to longer, and then decades for the traditional balloons. I would also test it with helium, since that's usually what balloons that are released are filled with. And then I would also try to mimic what happens in each environment, such as the waves and currents for the water environments. And finally, I would test multiple different brands for each type of balloon to see if the results are consistent across the board.